I welcome you all to the session of engine system and performance, and today we shall discuss about basic cycles, those used to analyze the performance of internal combustion engines, and thereafter we shall try to analyze those cycles just to estimate their thermal efficiencies. So, in the last class we have talked about engine classification, and we have seen that engine can be classified based on several points, several issues. The broad classification is based on the type of combustion and number of stroke that we have discussed. Now, given that both spark ignition engine and compression ignition engine, both engines have much in common, but still there are some fundamental differences between these two types of engines. So, an important difference is their analysis, and today we shall discuss that topic only, considering several cycles, rather basic cycles used to describe the processes or used to represent those processes which are there in SI and CI engines. So, if we first discuss about a 4-stroke cycle SI engine. A 4-stroke cycle SI engine, typically that 4-wheelers or 2-wheelers. Now, you have studied this in your undergraduate internal combustion engine course, still we shall discuss this just to recapitulate in this course again. So, if we try to recall the schematic depiction we had discussed in the last class, in a spark ignition engine, spark plug is there and that spark plug acts like an external agent to initiate the combustion. So, briefly if we try to recall, just drawing a schematic of so, this is the schematic depiction of a spark ignition engine. So, this is the spark plug, this is intake manifold, and this is exhaust manifold through which combustion gases leave out from the engine cylinder or combustion chamber. Now, in a 4-stroke cycle I am not going to discuss this, because the piston reciprocates between these two locations, top dead center and bottom dead center, and there are 4 different strokes. Intake, so intake stroke is piston travels from top dead center to bottom dead center, there is a valve in these two locations, exhaust valve remains closed, intake valve opens, and through this intake manifold, if it is SI engine, certainly it is not only the air, but the air fuel mixture, that is also known as charge. So, air fuel mixture will be drawn into the engine cylinder as the piston travels from top dead center to bottom dead center. So, that is the intake stroke. The next stroke is the compression stroke. Exhaust valve is remaining closed. When piston reaches at bottom dead center, intake valve is closed, and then the entire space is filled with charge which is drawn into the cylinder or combustion chamber during intake stroke will be now compressed as the piston moves up. That is the compression stroke. And when piston is about to reach at TDC, we need to switch on the spark plug, and assuming that it will take some finite amount of time to switch on the spark plug, and by that time piston will be reaching at TDC and entire charge will be combusted. So, the entire combustion will take place, and that is why as if the piston has reached at TDC and the compressed compressed charge which is now here in this space will be combusted. So, entire combustion will be will take place, and as if the volume is remaining constant. So, this is approximated as a constant volume combustion, and because of this combustion that is we will have substantial amount of energy in the form of heat, and pressure also will be there. So, that high pressure will create a thrust on the piston face which will allow piston to travel back from TDC to BDC again, and that is the power stroke. And finally, when piston will be reaching at BDC at the end of the power stroke, then the next stroke is the exhaust stroke, that is piston will again move off and exhaust valve will be open, and as the piston travels off, all the combustion gases will leave through the exhaust manifold into the ambience. So, this way 4 different strokes will be there, and these 4 different strokes will be or will get executed in a cyclic manner, because that reciprocating motion will be converted into the rotary one using this crank and connecting rod mechanism, and we can drive 2-wheeler or 4-wheeler. So, the question is that is fine, but to analyze essentially we are supplying air fuel mixture through this intake manifold into the combustion chamber. So, we are supplying certain amount of energy, and that is the chemical energy. That energy is remaining stored within the fuel. So, when we are trying to burn the fuel, that is the combustion, so we are again getting some sort of energy, that is energy in different form, that is heat. But again that energy is not available to the shaft of the engine. So, that means that heat energy will be again converted into work, and that work will be available to drive the 4-wheeler or 2-wheeler. So, question is, at the cost of some input energy, that is the chemical energy which is remaining stored in the fuel, we are going to get some other form of energy. So, we need to know what fraction of energy recovered is there, and to know that we need to quantify the thermal efficiency or mechanical efficiency of the engines. Forget about mechanical efficiency because you have studied all these things in your undergraduate course, but now what we can do, we can analyze the cycle and we can also calculate the thermal efficiency, that is the indicated thermal efficiency, that is the energy which will be available inside or at the top of the piston face. Okay. So, now to analyze this we need to know some cycle. You know that thermodynamic cycle, because we have studied in our thermodynamic course that Rankine cycle, then Carnot cycle, the most important ideal cycle, but the cycle that we will discuss today, these cycles are not called as thermodynamic cycles, because it is not the closed one. You can understand that the working substance that comes into the engine cylinder during intake stroke, that working substance will not be recycled. That working substance will be will take part in combustion, and because of this combustion we will be having several combustion gases, and those combustion gases will leave out from the engine cylinder through the exhaust manifold into the ambience. So, essentially the working substance is not getting recycled back. So, one of the most important criterion for a cycle to be called as the thermodynamic cycle is the working substance has to be recycled back. So, this is not there. Second thing is the composition of the working substance is getting changed. When we took air fuel mixture into the engine cylinder, it is air and also fuel, air fuel mixture, but after the combustion the composition will be different. So, composition is also going to be changed at the end of the cycle. So, this also contradicts that the cycles will be called as the thermodynamic cycle. So, but we can call these cycles as the mechanical cycles. Okay. So, what is the need? So, all these 4 strokes are there, 4 strokes will occur or recur consecutively, right, and what we could see that at the beginning and end of the stroke thermodynamic state of the working substance will be changed. So, to know the thermal efficiency or indicated thermal efficiency, we need to know pressure and temperature of the working substance at the beginning and end of each and every stroke. To know that, we need to compare these processes, we need to map these processes using several thermodynamic planes, and we need to adhere to any cycle just to compare or just to estimate the efficiency. So, all these processes are approximated by the air standard cycle for a 4-stroke cycle SI engines, and that air standard cycle is called as Otto cycle, which is named after one of the inventors of this type of engine, Nicholas Otto. So, let us now briefly discuss about these processes, rather if we can represent these processes in thermodynamic planes. So, if we try to represent these processes, so one of the most common thermodynamic plane is PV plane. Similarly, we also need to map these processes in another thermodynamic plane, that is temperature entropy plane. So, if we map the processes, let us start from TDC. When piston is at TDC, both valves are closed. As piston travels from TDC towards BDC, intake valve will open and exhaust is remaining closed, that is intake stroke. So, this is say and there is basically that naturally aspirated wide open throttle. So, in this case there is no any system that can boost off or that can be used as the pressure boost off of the intake air. Rather, travelling or movement of piston from TDC to BDC will allow air fuel mixture to be drawn into the cylinder. So, assuming that this is the pressure, so you can understand here the pressure is atmospheric pressure. If we now bring the piston down from TDC to BDC, inside we are creating some sort of vacuum, and that pressure difference will allow that pressure difference is the driving force for the air fuel mixture to be drawn into the engine cylinder. So, if we assume that this is the first process and say this is point 1. So, when piston reaches at BDC at the end of the intake stroke, that is the point 1. Then the next stroke is compression stroke. So, basically that it would be like this, because as I said you that in SI and CI engines we are trying to represent all the processes using an air standard cycle. In particular, for a 4-stroke cycle SI engine, we are trying to map all the processes using an air standard cycle, that is named as or called as Otto cycle. So, if we are trying to use an air standard cycle, we must assume that the working substance is air and we can apply ideal gas relationship. So, if that is the case, then process 1 to 2, that is, you know very well, isentropic compression. So, the process will be compression. So, as if both the valves are closed now, piston is travelling back from BDC to TDC and the entire charge is getting compressed. So, the process is a compression process and we can approximate that process by an isentropic compression, so that we can easily map here. Next 2 to 3, that I told you, that when piston is reaching a TDC, entire charge will be occupied in this place and spark plug switch will be on, and the spark that will be developed here will initiate the combustion and entire charge will be combusted, as if during that time piston is remaining there at TDC, though the movement of piston is spontaneous. So, this approximation allows us to consider that the combustion can be mimicked by a constant volume combustion. So, constant volume means the volume is remaining constant. So, you can understand it is because of this combustion, this pressure is P3 and this P3 is the maximum pressure in the cycle, right. And then at the end of the combustion, that I showed you that high pressure, high temperature, high pressure will create a thrust on the piston face, which will allow piston to go down again from TDC to BDC, and that is nothing but again expansion of the combustion gases inside the cylinder, and that expansion can be again mimicked by an isentropic expansion. So, this is the process, and finally, so this is 3 to 4 and then 4 that when piston is at BDC at the end of the power stroke, then we need to open the exhaust valve immediately, so that inside the cylinder high pressure gases will leave momentarily the when we open the exhaust valve. So, when combustion gases are leaving out of the or leaving from the engine cylinder, that gases will carry certain enthalpy. So, we will be having energy loss, heat loss. So, that is 4 to 1, and as if when piston is exactly at BDC, if we open the exhaust valve, that high pressure which is there inside the cylinder will allow the combustion gases to leave out, and when the combustion gases are leaving, mass loss is there, and that mass of combustion gases will basically will be having some enthalpy. So, that is heat loss. So, this is Q out. I am writing in terms of specific quantities, and this combustion is Q in, heat addition. So, that you have studied. So, now if we try to represent all these processes in TS plane, then let us map all these processes. So, what I said that 1 to 2, that process is isentropic process. What does it mean? The process is isentropic, so entropy will remain constant, because so if we map the process 1 to 2, right, and then 2 to 3, this is constant volume combustion. What is combustion? Combustion is nothing but an exothermic exothermic reactions. So, it is because of this process we will be having substantial amount of heat generation. So, that heat is as if this process is adding heat to the system. So, constant volume heat addition. So, if it is constant volume heat addition, you can understand pressure is becoming maximum and that heat also will increase the temperature. So, temperature also will be maximum. So, this is T3 and this T3 is T max, T3 is T max, and then 3 to 4, you can see that again 3 to 4 is basically expansion process. So, isentropic expansion. So, this is the process, and 4 to 1 that I said that heat rejection. So, when piston is at BDC, if we open the exhaust valve, momentarily certain amount of combustion gases will leave out, and with while the combustion gases are leaving, we are also going to have loss of enthalpy. So, that is basically heat rejection. So, Q out, and that it is because of this heat rejection, temperature of the working substance or the combustion gases will be less. So, eventually it will come to 0.1. So, this way we can complete the cycles. So, now these two are the representation of all these processes in two different thermodynamic planes. One is PV plane, another one is TS plane. So, from this now we shall try to quantify what could be the thermal efficiency, or later on we shall see that efficiency is basically indicated thermal efficiency. So, if we write now, so you know very well that thermal efficiency from second law we can write that W net by Q in. It is better to always represent in terms of specific quantities, that is per unit mass of working substance. So, if we know Q in and if we know W net, then we can quantify this. So, what is W net? So, W net is Q in minus Q out, right. So, that we can get from first law of thermodynamics, that is energy balance. So, you know that heat addition minus heat rejection, that is essentially the amount of energy you are going to get in terms of work. So, this is W net. So, if we write this expression in the next page, then we can write thermal efficiency equal to Q in minus Q out divided by Q in. So, basically you will be getting 1 minus Q out by Q in. We are writing, we will be taking only the magnitude, not the direction. So, what is Q out? You can see Q out is this. So, I am not going to discuss in detail because you have already studied this, but just to have the mathematical expression of this quantity, that is thermal efficiency, we are trying to discuss this processes. So, Q out is, this is constant volume heat rejection, right. So, Q out is CV into T4 minus T1. So, if we write, that is Q4 1, that is constant volume, specific it CV, this is specific quantity. So, CV into we can write T1 minus T4. And what about Q in? That is Q223. If we go back to the previous slide, you can see Q in, this is the Q in and this is the Q out. So, Q in is constant volume heat addition. So, CV into T3 minus T2, that is what I have written in the next page. So, CV into T3 minus T2. So, now using these two quantities, if we try to write the expression, then eta thermal equal to 1 minus CV into T1 minus T4 divided by CV into T3 minus T2. So, if we write one step further, 1 minus T4 minus T1 divided by T3 minus T2. So, it would be 1 minus T4 by T1 minus 1 divided by T3 by T2 minus 1 into T2 by T1, this quantity. So, this is the expression. Now, if we go back to the previous page, so 2 to 3 is basically 1 to 2 is basically what is the process? Isentropic compression. 2 to 3 is constant volume heat addition. and 3 to 4 is also isentropic expansion. So, can we write, now we have to have a relation between the temperature T1 and T2. So, again as I said you that we have assumed that the working substance is air, though it is not purely air, it is air fuel mixture, but you have studied these issues, the consideration or validity of this approximation, but it is mostly air, but it is not the pure air. So, what we assumed is we have considered the working substance is air, and we have approximated all these processes by an air standard cycle, and then we have also we also can use ideal gas relationship. So, from this we can write T2 and T1. So, we can write T2 by T1 equal to V1 by V2 power k minus 1, k is Cp by Cv. Okay. So, k is Cp by Cv. So, now it is very important that if we go back to the previous slide, see V1 and V4 same and V3 V2 same. So, instead of writing V1 you also can write V4, instead in place of V2 you also can write V3. So, just if we change it, that we can write V4 by V3 power k minus 1, and that is nothing but T3 by T4. So, just if we write one step further, then we can write T4 by T1 equal to T3 by T2. So, this will allow to write, if we go to the next slide, that means eta thermal equal to 1 minus 1 upon T2 by T1 into T4 by T1 minus 1 divided by T3 by T2 minus 1. But we have seen that T4 by T1 and so this will get cancelled because T3 by T2 equal to T4 by T1. So, we are left with 1 minus 1 upon T2 by T1, and what is T2 by T1? T2 by T1 is equal to V1 upon V2 power k minus 1. So, that is equal to 1 minus 1 upon V1 up by V2 power k minus 1. So, this is known as compression ratio power k minus 1, because V1. So, V1 is when piston is at TDC, that volume corresponds to the volume when piston is at BDC, and V1 corresponds to the volume when piston is at TDC. So, this VTDC by BDC is known as compression ratio, right. So, as if we are trying to compress the volume. So, this is basically BDC, VBDC, and this is VTDC. So, as if we are trying to compress the volume from VBDC to VTDC. So, the ratio of VBDC by VTDC or VBDC to VTDC is known as compression ratio RC. So, what we can write RC power k minus 1, where RC equal to VBDC by VTDC. So, what we can see from here that if we try to write the indicated thermal efficiency versus compression ratio. Now, why it is indicated thermal efficiency? Because you know that we have estimated this efficiency considering the heat transfer to or from the air inside the engine cylinder. So, this is the efficiency which is indicated one. See, this is not the efficiency which is available at the shaft of the engine. I mean, this efficiency is not calculated considering the energy which is available at the shaft of the engine. Rather, this efficiency is calculated based on the fact that, or based on the energy transfer or heat transfer to or from the air of the engine cylinder. So, this is the indicated thermal efficiency. Now, when RC equal to 1, then when RC equal to 1, efficiency equal to 0. So, 1. Now, it will be like this. So, this is the curve eta thermal versus RC. So, if we increase the compression ratio, efficiency will increase, that you can see. So, if we increase RC, efficiency will increase. Okay. So, this is all about the thermal efficiency of 4-stroke cycle SI engine. So, let us quickly discuss about four-stroke cycle CI engine. So, again if we just draw the schematic, so this is only air, so this is only fuel, so instead of spark plug, we are now having a fuel nozzle through which fuel is injected. So, what is the fundamental difference here is that since fuel is supplied, fuel is nothing but composed of several hydrocarbons, and because of several hydrocarbons, if and that too there is no spark plug, what is done that when piston is reaching towards TDC during the compression stroke, so the compressed temperature which would develop due to compression of the air, that temperature itself will allow fuel to ignite when fuel is sprayed into the combustion chamber. Now, so fuel composition, depending on the fuel composition, an ignition delay will be there. So, basically physical delay plus chemical delay, that is the total ignition delay that you have studied in your undergraduate course. So, because of this ignition delay, what is done that when piston is about to reach towards TDC, fuel is sprayed. So, when fuel is sprayed, that fuel will initiate, or that fuel will be combusted. So, that is known as first phase of combustion. So, when piston is yet to reach at TDC, fuel will be sprayed, first phase combustion will be there, and it is because of this first phase combustion some pressure will develop, and when piston will be reaching at TDC, still combustion will be there, and because of the chemical delay or ignition delay, when piston will be leaving from TDC towards BDC during power stroke, still certain fuel will be there for combustion. So, late phase of combustion. Considering all these, it is not possible to mimic the combustion by constant volume process, because combustion will start when piston has not reached even at TDC, combustion will continue when piston will be reaching at TDC, and it will last even when piston is leaving from TDC towards BDC. So, during this process volume is remaining no longer constant, rather because of this first phase of combustion some pressure will be there, and then again another combustion will be there, though the piston is coming back from TDC towards BDC, as if the pressure is remaining constant because of several phases of combustion. So, that is the fundamental difference. So, here the combustion process cannot be mimicked by a constant volume process, rather it is mimicked by a constant pressure process. So, if we try to draw the pressure volume diagram and TS plane and processes in TS plane. So, if we try to draw the processes in both PV and TS plane, so the same process. So, this is one, and then this is the compression process. Now, it is not the constant volume, rather constant pressure combustion, and then finally, so this is 3, this is 4, this is 1. So, 1 to 2 is isentropic compression, 2 to 3 is Q in, that is constant pressure combustion, 3 to 4 is again isentropic expansion, and 4 to 1 is heat rejection, that is blow down. So, when piston will be at BDC, if we open the exhaust valve, momentarily certain amount of gases will leave from the engine cylinder to the ambience through the exhaust manifold, and those gases will carry certain amount of heat, or that is why we are assuming that is called constant volume heat rejection. Similarly, if we try to draw the processes in TS plane, you can see that 1 to 2 isentropic. So, this is isentropic process, isentropic compression, then 2 to 3 that is constant pressure combustion. So, here temperature will be maximum. So, this is 3, and then 3 to 4. So, this is the blow down. So, T3 is T max and P3 equal to P2 equal to P max. So, this is what we can see. So, again if we try to write the kind of thermal efficiency of this particular cycle, just I am trying to write eta thermal indicated. Why it is indicated? Because we are trying to quantify the efficiency considering the heat transfer to and from the air of the engine cylinder. So, air or working substance that is there inside the engine cylinder, from the air or to the air we are trying to calculate the heat transfer, to the air because of combustion and from the air because of this blow down. So, this is again following the previous step, we can write 1 minus Q out by Q in. One thing we will discuss here, that if you try to recall, during the combustion process volume has changed, volume of the working substance has changed. So, we can define one ratio that is called cut-off ratio. So, cut-off ratio is beta equal to, this is defined as V3 by V2. So, cut-off ratio beta, which is defined as the change in volume that occurs during combustion process. So, volume has got changed from V2 to V3, and this ratio of V3 and V2 is known as cut-off ratio, because the volume of the working substance has got changed. So, basically as if we try to express the, or if we try to quantify the thermal efficiency using W net by Q in. So, W net while we will be calculating, we also need to take into account the work done during this process, right. So, cut-off ratio is defined as the change in volume that occurs during combustion process, V3 by V2. Okay. So, if we now try to write this Q out, what is Q out? So, Q out equal to 1 minus CV into Q out, CV into T4 minus T1, or T1 minus T4, T1 minus T4. So, that is mod by Q in. Q in is, it is Cp into T3 minus T2. It is this constant pressure. So, this is basically constant pressure heat addition. So, this is constant pressure heat addition. So, if we write one step further, we can write 1 minus 1 upon Cp by Cv, and then we can write T4 by T1 minus 1 by T3 by T2 minus 1, then 1 upon, this is T2 by T1, right. So, we can write 1 minus 1 upon k and T 3 by T 2. So, if we write T 2 by T 1, so T 2 by T 1 equal to V 1 by V 2 power k minus 1. What is V 1 by V 2 again in terms of compression ratio? So, this is V VDC this is VTDC. So, what we can write that is nothing but V BDC divided by VTDC power k minus 1. So, that is RC power k minus 1 compression ratio. So, this is the compression ratio. Compression ratio of the engine. So, we can write k into RC power k minus 1 and then within bracket we can write T 4 by T 1 minus 1 divided by T 3 by T 2. So, what is T 3 by T 2? So, V 3 by V 2 that is constant volume process. So, this is nothing but T 3 by T 2, right. So, we can write that V 3 by V 2 is equal to T 3 by T 2. So, this is beta minus 1 cut-off ratio. So, this process constant pressure process. So, if we apply Ayer's ideal gas relation, then beta equal to V 3 by V 2 equal to T 3 by T 2. So, that we have written. Now, if we just write this steps further, one step further, then we can write eta thermal equal to 1 minus 1 upon k, or we can write this is RC power k minus 1 T 4 by T 1 minus 1 divided by beta minus 1 into k, right. This is what we can write. Now, what about T 4 by T 1? So, what is T 4? If we try to go back to the processes, so we can write T 4 in terms of T 3 and T 1 in terms of T 2, and if we can write T 4 in terms of T 3 and T 1 in terms of T 2, then you also can express that quantity in terms of beta, because beta is already T 3 by T 2. So, if we write here T 4 is equal to how much? T 4 is equal to T 3 into V 3 by V 4 power k minus 1 divided by this is T 2 into V 2 by V 1 power k minus 1. That is nothing but T 3 by T 2 into V 3 by V 4 into V 1 by V 2 power k minus 1. Since V 1 equal to V 4, V 1 equal to V 4, that you can see from this PV diagram, V 4 equal to V 1. So, then what we can write, this will get cancelled and eventually V 3 by V 2 is equal to again T 3 by T 2. So, T 3 by T 2 power k, and that is beta power k. So, we can write this expression equal to 1 minus 1 upon RC power k minus 1 beta power k minus 1 divided by k into beta minus 1. So, this is the expression of mathematical expression of thermal efficiency of 4-stroke cycle CI engine. Now, one thing I forgot to tell you, that to compare the performance of a 4-stroke cycle SI engine, we have discussed about an air standard cycle, and that air standard cycle is called as Otto cycle. Similarly, the processes of a 4-stroke cycle CI engine are approximated by an air standard cycle, because we have applied ideal gas relations, assume that the working substance is air and that cycle is known as diesel cycle. So, eta thermal diesel. Dr. Rudolf Diesel, who first invented this particular type of engine, and to honor the name of that's to honor the name of Dr. Rudolf Diesel, this cycle is called as or named as air standard diesel cycle. So, now what we can tell from here that K is always greater than 1, beta is always greater than 1, because T3 is always greater than T2. Now, the quantity given in this bracket is always greater than 1. So, for a given compression ratio, if we try to compare the thermal efficiency of diesel cycle or diesel engine, which is always less than the thermal efficiency of 4-stroke cycle petrol engine or 4-stroke cycle SI engine. Now, since diesel engines are typically having higher compression ratio, hence 4-stroke cycle CI engine or CI engines will always have higher thermal efficiency than 4-stroke cycle SI engines. So, to summarize today's discussion, we have discussed about the basic cycles typically used to map several processes of both 4-stroke cycle SI and CI engines, essentially to estimate their performance efficiencies. And then we have briefly discussed about several processes in different thermodynamic planes, and from there we have tried to quantify the mathematical, or we have tried to express the mathematical form of thermal efficiency, that is the indicated thermal efficiency of both 4-stroke cycle SI and CI engines. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.